Today we are going to be learning about section 11.6 in your books. It is areas of regular polygons and is on page 762. The key first is that we're going to develop a formula for the regular polygon, and we're going to develop it from known formulas, so from previous knowledge. And what we do know about regular polygons is that they are made of polygons that have congruent sides and they have congruent angles. So that's what a regular polygon is, and we want a formula for the area for that regular polygon. So we already know the area of a triangle, we already know the area of a square, and what we want to do is develop an area formula for all the rest of the regular polygons. So we're going to start with the regular pentagon. We want to break it up into shapes that we know the formulas for. So we know the formulas for a triangle, we know the formula for a square, for a rectangle, for a kite, parallelogram, rhombus, trapezoid. So we want to break up our regular pentagon into some of those shapes. The easiest would be to go from the center of your regular pentagon and to break the pentagon into congruent triangles. From the center, we could make that into 5 congruent triangles. For a regular hexagon, we could break that up into 6 congruent triangles. And then we could back up and go to the square. We could make that into 4 congruent triangles, and with a triangle we could make that into 3 congruent triangles. Alright, with that, we're going to develop the formula for a regular polygon. So starting with a triangle, we're going to make this into 3 congruent triangles, and so on, 4 congruent triangles. And so when you have a regular n-gon, there would be n congruent triangles. We know the area formula for a triangle, that's why we chose this. This is 3 times a 1/2 base times height. And so the general formula would be n of these triangles. Alright, now our job is to change the triangle information into a polygon information. So I'm going to start with the triangle that we're talking about here. Let's take it in this pentagon. It has a base, but the base is of the triangle. That base of the triangle is the same as the side of the polygon. So we're going to name this base, which was B, we're going to name it an S. So in all of our formulas, we're going to change all of our B's to S. And then we're going to rename the height of the triangle. So the height right now comes from the center and it's perpendicular to the base of the triangle. But this is with respect to the triangle. We want to name this length with respect to the polygon. So I need to scroll down here. It's a new word. It's called apothem. Apothem comes from the center perpendicular to the side. So you say that, it kind of sounds like a possum, but you have a apothem. So get the thumb in there. Alright, so the definition for an apothem is a segment from the center of a polygon perpendicular to the side of the polygon. That's the definition. So this, going back up, this perpendicular, which we called a height in the triangle, is called apothem. We use A for apothem in the polygon. So we're going to rename all of these formulas now. I'm going to switch the 1/2 and the 3 around. I'm going to have 1/2 times 3 times change the base and name it as a side of the polygon. Change the height of the triangle, name it apothem. So I'm going to do the switches all the way through. Bring the 1/2 out 4 times the side, because I'm changing my base and naming it as a side, changing my height, naming it apothem. That's a 5. And then we have times side, it's an S, times your apothem. Alright, so finally, when you get to the regular n-gon, you have a 1/2, and then you have n times s times a. So this is the developed formula for any regular polygon, and it's developed by congruent triangles. Now we can rename it a little bit. If we talk about the perimeter of a regular n-gon, let's do a hexagon. So if I have a regular hexagon, to find the perimeter, since all the sides are the same, and because it's a hexagon, you're going to say that the perimeter is 6 times the length of each side. So it would be 6x, 6s. If you're doing the perimeter of any n-gon, then the number of sides there would be n, and the length of each side would be s. So the perimeter of a regular n-gon is the number of sides times the length of each side. Perimeter equals ns. Now you could then use the area formula for a regular polygon to be, if I look from up above here, this ns is the same thing as the perimeter. So the area could be renamed as 1/2 perimeter times apothem, because right here this perimeter is the same thing as up above n times s. So you can remember both formulas for the regular polygon. Okay. Next, how can you find the missing lengths of these regular n-gons? If we go into the regular hexagon, or any n-gon, let's just say that the things that you're going to need to find to fit your formula is going to be the apothem, which is perpendicular to this side, and you can make a right triangle. This side you'd only use half of it, and then you could find the radius of the hexagon. But really, the only two parts that you are looking for are the apothem and the side. The side will help you come up with the perimeter, because it's number of sides times the length of each side. Okay, here's how you can come up with those two missing parts, the apothem and the side. You drop the apothem and you form that right triangle. You're going to have two congruent triangles right here. They're congruent by these two radii of the polygon are congruent. This is congruent to itself, reflexive, and then you have a right angle. So these two triangles are congruent by hypotenuse leg HL. And since those two triangles are congruent, you can find this interior angle and then divide it by 2 to find one of the angles, which then you can go ahead and use trig or any of these other right triangle methods. So here are the right triangle methods that you could use. You can use the Pythagorean theorem, which is a squared plus b squared equals c squared. You could use any Pythagorean triple, and these are the family names or any multiple of them. You can use a 30-60-90, which is x squared is 3 and 2x for the sides. You can use a 45-45-90, which is x, and x times the square root of 2. And then you can use trigonometry. You can use SOHCAHTOA. So if you have a right triangle, you can take the sine from the angle and compare the opposite side to the hypotenuse. Or you could take the cosine from the angle and compare the adjacent side to the hypotenuse. Or you could take the tangent from an angle, and there you'd be comparing the opposite side to the to the adjacent side. So that's your trig method. Alright, we're going to stop here for part 1, and then I'm going to pick up doing examples on the part 2.